Alright, so first off, I'm going to try doing some videos that are a little quicker, a little to the point, more. You're going to get the same amount of content, I just might break it up in more videos. So for example, this section we're talking about the Lorentz transformation, and I'm going to break it up into a couple videos instead of like one really big video or two really big videos. Maybe it'll be 4 or 5, so hopefully you guys like that a little more. So we'll start off by, if you remember, here's a picture, the Galilean transformation. We talked about this in the first video. When we have one fixed frame of reference and one moving frame of reference going at a constant velocity, we have a Galilean transformations over here, which work really, really well at low speeds. The problem is the Galilean transformations, so we'll put the, let's make this a little bigger. So the Galilean transformations fails at high speeds. Okay. So we need a new set of equations that work and describe reality even at high speeds. So a few things to note. We need equations that are one, they are consistent. Oops, pen's acting up. Consistent. They are consistent with Einstein's postulates. Okay. Number 2, they need to simplify to the Galilean transformations when u approaches, well, we won't say u, we'll say when c is, see if I, there we go, much greater than u. Okay, so let's go ahead and give you the equations. So this is for assuming we're moving in the x direction. X prime is equal to x minus u over t divided by the square root of 1 minus u squared over c squared. Y prime is just y. Z prime is just z. And t prime is equal to t minus u over c squared times x all over the square root of 1 minus u squared over c squared. So here we go. I guess they're worth boxing in. If I can box them in. There we go. Here we go. There's our transformations. Real quick, we assume O prime moves away. Did I say U prime? O prime moves away from O. Kind of like in the picture here. If O prime moves towards O, and all you need to do is replace U with a negative U. And sometimes we can write these, we can write in terms of the time intervals, or the intervals in general, like delta x, delta t, etc. And then the last thing I want to do is note when u is much smaller than c. Well, if we look over here, if u is much smaller than c, then that's just x prime equals x minus u over t divided by the square root of 1 minus a small number divided by a really big number. That's almost 0. So it's really just x minus ut, and this is our Galilean transformation. So at low speeds, it transforms. It breaks down to our kind of common sense thought process. And for the time, t prime equals t minus basically 0, using the same logic as before, times x, and again the square root of 1, because so this is basically 0 and this is basically 0. So that is just t prime equals t. And this is just an assumption that they'll have the same measurements for time. Right over here it breaks down. It simplifies just to what we saw before. Now we can continue to use this to show and predict properties that we've seen when we dealt with the consequences of special relativity, such as length contraction, which we'll get into next. But for now, I just wanted to do a basic introduction, so hopefully that